Hello, welcome to our first press conference of the 2015 AGU Fall Meeting. Epic first results from the DSCOVR satellite, an unprecedented view of sunlit Earth. Our speakers are Bob Smith, DSCOVR Deputy Project Manager, NASA Goddard Space Flight Center, Jay Herman, Research Scientist, University of Maryland, Baltimore County, and NASA Goddard Space Flight Center, Alexander Marshak, DSCOVR Deputy Project Scientist, NASA Goddard Space Flight Center, and Stephen Lorenz, NISTAR Instrument Lead Investigator, L1 Standards and Technology Incorporated.
Good morning. My name is Bob Smith, and for the last 3 years I've been the Deputy Project Manager for the DSCOVR mission. And I'd like to start by making a comparison between DSCOVR and the Hubble Space Telescope, not because DSCOVR is a great observatory, but because we're going to do something for the very first time, and that is to go out to the first Lagrange point and look back at the Earth as a planet. And we expect to find things that we didn't have in our list of mission objectives when we do this, because anytime you do something for the first time, you always find things that you didn't expect. So I will give an overview of the mission itself, and then Jay Herman will provide some images that haven't been seen by the public before. Dr. Marshak will give us some very interesting things that we found that we didn't expect, and Stephen Lorenz will provide some information on the science that he's collected that'll be applicable to the very important question of climate change. So I'd like to thank our sponsors. NOAA has paid NASA to bring DSCOVR to the launch. And then the U.S. Force provided the SpaceX Falcon 9 launch vehicle to get us onto orbit. So the launch occurred at Cape Canaveral Air Force Station. We had a couple of mid-course correction burns, and then we went into our Lisa Ju orbit insertion burn, and now we're orbiting around the first Lagrange point, which is 1 million miles or 1.5 million kilometers from Earth. At that point, it's a great place to monitor the solar wind, and NOAA will use that information to provide space weather forecasting using the Plasmag instrument suite, which includes a magnetometer, a Faraday cup, and an electron spectrometer. So looking back at Earth, we're going to image the sunlit disk of the Earth in 10 different spectral bands using the Earth Polychromatic Imaging Camera, or EPIC as we call it, and then we're also going to measure the energy coming from the Earth using the NIST Advanced Radiometer, or NISTAR. And then we have an experiment called the Pulse Height Analyzer that's measuring cosmic rays. This is the sun-facing side of the spacecraft in our clean room at Goddard Space Flight Center when we were doing our integration and test. You can see the black solar rays that provide the electrical power to run the spacecraft. The bottom is a circular structure to house the propulsion module. On that, we have in this bag a 3.5 meter deployable boom that had the magnetometer on the end of it. Next to it is the electron spectrometer. We have some red removed before flight covers for delicate things like our thruster modules and the digital sun sensor. This is the backside of the EPIC instrument. Under this red cover is the Faraday cup. The star tracker for providing attitude information is here. And then around the front side, you can't see it, is the NISTAR instrument, but Dr. Lorenz will have a great picture of that later in the presentation. So after a very exciting and long day, SpaceX launched us on their Falcon 9 rocket on February 11th of this year and put us on a very excellent trajectory towards L1, and also gave us some very nice photographs as well of the launch. So this is us on leaving the transport erector structure, and then these structures here are for lightning capture, so that if there were a storm, we wouldn't get electrocuted. So in this graphic, I'm going to show our trajectory to L1. If you look down from the north ecliptic pole, you'll see this view with the Earth here and the first Lagrange point out there. In this view, it's looking in the ecliptic plane as if you were following the Earth around its orbit around the Sun. And then if you were at the Sun looking back at Earth, this is the view you would have of the spacecraft coming out towards L1. If I can find the mouse, I'll get it started. Okay, there it is. So we very quickly passed the orbit of the moon, which is this circle here, and then we entered into this arcing path here that is very similar to what you would see a snowboarder do in a half pipe. We went out to a 37-degree loop, came back around, and then when we crossed the ecliptic plane, we did a 4-hour Lissajous orbit insertion maneuver burn that put us into an elliptical orbit around the first Lagrange point. Now this orbit will be in an ellipse this way, and then it will transition back to a circle and then an ellipse this way. And then eventually it'll cross through this white circle here, which is the 4-degree solar exclusion zone, which may cause us to lose telemetry because of the radiation coming from the sun will swamp the telemetry signal coming back from the Earth, or from the spacecraft. So the overall spacecraft status is doing great. We've got pointing and stability that is much more stable than we thought it was going to be. So this is allowing us to get epic images that are very close to their theoretical optical resolution that we had calculated by the instrument itself. So that's really amazing, and we can see some great stuff that we'll see later in the presentation. We have more than twice the power that we were required to have at launch. The very accurate launch trajectory means that we will have enough fuel that it's projected to last until 2029. And we've finished our spacecraft commissioning activities. The NASA part's done. We handed over our operations to NOAA right before Halloween. And with that, I'm going to hand over the podium to Jay Herman.
Hi, my name is Jay Herman. I'm the EPIC instrument scientist, and both Bob and I have been part of this project since 1998. Let's see if I can get this to go. And what I wanted to show you here is first a cartoon of where the EPIC and DSCOVR spacecraft are located at Lagrange 1, about 1.5 million kilometers from Earth, or 1 million miles. And the one thing I want you to imagine is you're sitting there at L1, the sun is behind your head, and the Earth is sitting right in front of you, always rotating, so that you see the sunlit face of the Earth. And this may seem obvious, but to most of us, this is a hard concept to get used to, that the sunrise and the sunset are always visible in these images. There was a period a few years ago when we took this instrument out of storage and we refurbished the instrument, and we made some major changes to the instrument. We improved some of the optical characteristics, but the most interesting thing is we added 2 channels that are quite unique to this instrument: the oxygen A band, which is an absorbed band by oxygen in the atmosphere, and the oxygen B band. And this enables us to do some interesting science, a little bit of which I'm going to show you in a few moments. All this is accomplished using the moving filter wheel that's shown on your lower left. Now, most people haven't seen what the Earth looks like in these different filters, so I created a small movie showing this. And it's a self-starting movie, so this is the 780 channel. This is the strongly absorbed oxygen A band, B band. And then this is green, and then, I'm sorry, that was red and green and blue. And now I'm going into the ultraviolet, which is something that people mostly haven't seen. As you notice, we get into the far ultraviolet, this haze comes up. That's what's called Rayleigh scattering. Everything gets very dim. In order to do science, the Rayleigh scattering has to be removed in order to see ozone and other features. This is the longest wavelength channel that you just saw. The Earth is very sharp because of the lack of scattering. The EPIC camera was designed always to keep the Earth in the field of view. And so the field of view is just slightly bigger than the Earth. In this case, it's 0.62 degrees. The Earth occupies about 0.45 to 2.55 degrees, so we can center the Earth on the CCD most of the time. This is one of the frames from a movie that most everyone has seen, of the moon passing in front of the Earth. I'm not going to show the movie of this one because it's been seen so many times. However, I did create a new movie. We usually use the moon for calibration. We stare at the moon, and there was an eclipse. And in this case, we stared at the moon as the Earth moved in front of the moon. About 4 hours before, we saw the eclipse from the Earth. And that's because we're at an angular position just to the side of the Earth-Sun line, so we see a slightly different eclipse than the Earth would. I'll let this one run. The Earth is rotating as it goes by. It's really kind of neat. You can actually watch the motion of the clouds as this happens. I'm going to let this one run twice. And if you pay very careful attention, you can see that the Earth is just slowly rotating around. This is about a 4-hour sequence. Okay, but one of the things that's of interest in the case of EPIC is, in addition to the spectacular images with the clouds, is what science we can do. And the science basically is ozone, which I'm not going to show because there's still some difficulty with the calibration. But this is an example of aerosols going across the ocean. When we get more of these images done, you'll actually be able to see the aerosol plumes propagate across the ocean into South America and the Caribbean basin. Not as you see it from low Earth orbit, where you only see it at a particular fixed time, but you'll be able to see it during the whole day, from sunrise on your right to sunset on your. Sunrise on your left to sunset on your right. So this is going to be extremely interesting. You'll be able to see smoke, dust, and volcanic ash very easily this way. Another very interesting thing is what's called the reflectivity. In the ultraviolet channels like 340 and 388, the Earth background is dark. Land has very low reflectivity, so do the ocean. So the clouds really stand out. And you can watch the change in the amount of cloud structure that's on the Earth, and this is related very closely to the Earth's energy balance. In the upper center, you can see Greenland sticking out as a bright image. But one of the things that's interesting is it's very difficult to see whether clouds are over the ice. In the next slide, this is a color image also showing the clouds over Antarctica, and once again, you can't see them. One of the things that came out of using the oxygen A-band is that it can separate clouds over ice. And I put this together just this last week. This is an image. This is a reference channel for 780 nanometers where you don't have the absorption. On your left is the 764 where you have the strong oxygen absorption. I changed the brightness so that on the lower panel so that you can actually see the clouds over Antarctica. And unlike the visible image a few moments ago, you can actually see where the clouds are. And this also is very much related to climate change and the amount of reflectivity that comes off of the Antarctic ice sheet. And just to finish up, this is an interesting movie that I put together of the Earth rotating for 24 hours. And at the very end of this, you'll see 3 storms in the Pacific, which I'll point out to you when this image stops rotating for a moment. There you see Africa going by. There's a storm in the Atlantic Ocean, and we're going to come up in a moment. It's extremely interesting. We actually got 3 storms. You can see them there, the little circles in the middle of the Pacific. And thank you very much. Now I'd like to bring the next speaker up. That's Dr. Alexander Marshak.
Yes, good morning. I'm Alexander Marshak from NASA Goddard. I'm the deputy project scientist. And because of a special location and the unique viewing angle compared to low orbit and geostationary satellite that we used to work with, every day brings us something new and unexpected. And with science team, we are trying to study these features and to separate real physics from instrumental artifacts. And I will show you 3 examples that we found pretty interesting. And I will start with a ship track observation from 1 million miles. And ship tracks are clouds formed around the exhaust released by ships. And so this is the image you saw from Jay's presentation, but rather than focusing on the moon, I will focus on ocean area west of Oregon and Washington. So what we see there if I zoom this, we see a bright line that is more reflected ship tracks. And this was very surprising for us that we can see it from 1 million miles. And it's even better seen if we go to a longer wavelength because of a strong contrast with dark ocean. And interestingly, compared with the low orbit satellites like MODIS for the same location, but and almost the same time, but very different viewing angles. So we see also ship tracks, but they look very different. Yes, indeed, from 1 million miles, we will be able not only to observe, but to study ship tracks. And my next example is cloud height estimate. Cloud height is very important for Earth's energy budget because it determines the ability of clouds to trap outgoing heat. And to estimate cloud height, as Jay already mentioned, we will use absorbing bands, oxygen absorbing bands, and because of absorbing atmosphere, clouds that are low, they are pretty dark, and comparing with a reference channel, we can see and estimate cloud height. And yes, we will be able to estimate cloud height daily cycle of cloud height. This will be a unique product from sunrise to sunset. And my last example is about sun glint. Sun glint is an optical phenomenon when sun reflects off the ocean surface at the same angle as satellite views it. And if the oceans were as smooth as a mirror, then nearly perfect sun reflection will be seen in satellite image. However, oceans are never smooth because of waves, radiation scattered in all directions, and gives a kind of wash-out appearance. And what is also important that if the ocean surface is very turbulent, then we see no glint, and I will show example of it. So let's go to the middle of Indian Ocean, and what we see here, a feature that there is a piece, there are two features I want to grab your attention, just dark ocean, and then a multicolored from more reddish to more bluish. Is it real, and why is that? So I zoom this, and then if we compare it with low orbit MODIS that we get used to, and so this is a bright glint area, and indeed next to it we see no glint. And if we zoom the MODIS image, that we see that area west from this glint is very turbulent and very wavy. And that is actually, and why is that? So because of equatorial countercurrent, and then exactly at this spot, we see that that current goes eastward and usually 10-15 meters deep, but sometimes it reaches the surface and creates a turbulent ocean surface. And because and why multicolored? But this is more instrumental because we have 4 minutes difference between blue and red channel. And when red channel gets a glint, and then blue channel can get a very turbulent area with no glint. And this is not a rare case, and these are 5 examples from October, and we see at the same place, if it's not covered by clouds, the same glint. And this is a little bit south, so it's north of Australia, where also we have equatorial countercurrent. And to summarize our expected product, what Jay already mentioned, UF reflectivity, and he mentioned aerosol property in UV. So, and I mentioned cloud height. We will also provide global ozone levels and vegetation and leaf area properties. Thank you, and let me introduce Steve Lawrence, who will tell you interesting, exciting stuff about NISTA instrument.
Good morning. I'm Stephen Lorenz from L1 Standards and Technology. Whoop. One quick reprise. When this mission started, I actually had blonde hair, and so it's been a while.
I didn't.
The DSCOVR provides a very unique opportunity. One of the simple questions that hasn't been answered very well in science, especially relating to climate, is we have a star, we have a planet, they interact, and all the measurements to date don't do a good job of getting just the integral value of what is the total reflected sunlight, what is the total global thermal emission. And the goal of NISTAR was to, DSCOVR allowed us a vantage point where we can actually do a very simple measurement. Unlike the beautiful pictures you see, they have 4 million pixels. I only have 4. One is a simple photodiode, unfiltered. And then there are 3 electrical substitution radiometers. The first band A is intended to measure the total energy coming from the planet. That's combined both the solar reflected at all wavelengths as well as the thermal energy at all wavelengths. Band B gives us the total solar reflected. So there's a filter that cuts off about 4.5 microns, and so we get all the energy from UV out to about 4.5 microns. And as you can see on the plots over here, that's sort of the important crossover between the thermal signal and the solar reflected signal. Band C is intended to pursue a particular question with regards to the effects of clouds and the difference, spectral difference in reflectivity of clouds. The instrument was designed to meet the goals of just a very simple experiment. We have a star, we have a planet. As a whole, just standing back and looking at that planet, how much light do I see? What comes off? And L1 provides a great place to do such tests. The rest of the talk, I'd like to focus on the data from the photodiode channel. It provides some interesting clues as to the effects of the incident angle from the sun and the tilt of the Earth. The data shown right here is the sum total of all the data that we've collected, uncorrected, that's just raw data, from the photodiode channel since launch. It's sampled at a fairly high rate. It's about 10 times a second. And this looks like it's actually a really horrible detector design, that we really missed something. But the detector itself in the measurement circuit has a signal to noise of 50,000 to 1. Everything you see here is actually real changes, either due to a change in the distance between the spacecraft and the Earth, or the Earth and the Sun, or the tilt of the Earth, or where the instrument is around its solicitude orbit. So if we remove those gross effects for distance, I'm sorry, one thing I wanted to point out. Here you see 4 corresponding slides. Now, this is a view back in June that we had, where we're actually looking. You can see these images are all at the same, taken at the same local time. You can actually see over the poles, over the North Pole here, so you can see some sea ice and a lot of clouds. In these next 2 images, the planet and the spacecraft are both aligned so that we're looking much more normal to the axis of the planet. And in the last one, the Earth is now tilted. So this image was taken from December 10th. We're now nearing the winter solstice, and the planet's at maximum tilt in the other direction. And it allows us to collect a lot of data. A lot of the signal now corresponds to the ice sheet from Antarctica. So in this one, if by removing the gross effects of distance and so forth, we're left with this. This is the same data set. And you can see that in July, the green box, The signal in the photodiode channel actually changed the mean value, the daily mean, changed 15% over that time. And then as we near the winter solstice and start to bring Antarctica into view, the signal goes back up. So for the photodiode channel in November, December, we saw a 16% change. Now, however, the total channel that measures all the radiation coming back from the planet only changed 2%. Even though the solar reflected goes up, since we now have a mean colder scene, the thermal emission is actually less. So they in this case, they somewhat balance. Band B reports 17% for the solar reflected, which matches pretty close to the photodiode, and band C shows actually a higher number of 21%. Now, if we expand the scale a little more time-wise, these are the very same data set, but expanded I think October and then late November. So these are simply 4 days. Now, all of the wiggles in the structure you see there are actually real. They're related to clouds forming, to changes in clouds as the planet rotates. The large oscillations, of course, are simply the rotation of the planet. But one takeaway here is the mean value here is significantly different than here. And as you can see in the image, the effect of the Antarctic ice sheet is becoming much more prominent. Now, simply looking at 3 points along the main oscillation, there's, this is, the minimum is around the Pacific. The maximum is very consistently with Africa in the center. And then this is about 4 or 6 hours after, I'm sorry, it's more like 6 or 7 hours after, where we're now bringing South America into view. And so we're starting to fall down the curve again. But with this instrument, we get a very direct measurement of, it's very easy to see that if there was no ice, the planet, the amount of energy lost to space would change dramatically. And before we move to questions, I just have one really quick comment. These pictures are just incredible. I remember cutting clippings out in the 60s and 70s of anything that showed up in the press. And I remember the early Apollo pictures. And so it's been just marvelous to see these. But there's a line from a Billy Idol song, probably didn't expect to hear that in this time, that you can only see how much the Earth is burning from space. Thank you.
Thank you. And now we will take questions. If there are any reporters in the room who have questions, please raise your hand and state your name and your affiliation. Are there any questions in the room?
Paul Doherty from the Exploratorium. And the first question I had was the oxygen A band gives you the heights of the clouds. Is that because you're looking at the absorption of the oxygen molecules and they're more absorption when you come down to the ground versus altitude, or how do you tell the cloud height?
That's correct. The oxygen A band has strong absorption, so it doesn't see as deeply into the atmosphere, and it's always done in reference to a band that does see all the way to the ground. So it's usually an adjacent channel, and the ratio of the two can be converted into cloud height as soon as we complete all of the calibration studies that we're now performing.
And another question for Robert Smith. March 9th, 2016, there's a total solar eclipse in the middle of the Pacific, and it seems you have a nice viewpoint if the moon doesn't get in the way. Do you know yet if you'll be able to see the eclipse shadow on the Earth for that event?
Well, as I said earlier, that we've handed over operations to NOAA. I don't know if, Jay, if you guys are involved in any of the science planning that may have been looking to take this into account. We're taking images about every 2 hours, so we should be able to see anything that's going on as far as the moon going in front of the Earth.
Yeah, one of the theoretical studies we did actually shows the shadow of the moon across the Earth, but we have not yet been in such a position where we see an eclipse crossing the Earth. What we have seen is the moon going in front of the Earth from our viewpoint, but not the shadow. And that's just because of the geometry we happen to be in at the particular time.
Are there any other questions for people in the room?
Hi, I'm Irene Klotz with Discovery Channel. I have two questions. The first is for Dr. Herman. Could you explain a little bit more about how you're able to make out those the features that are telling you that they're related to ships? Because I'm sorry, to my extremely untrained eye, it looks just like clouds.
That question should be directed to Dr. Marshak.
Oh, okay. And then the other question, which is maybe for anybody or a few of you who'd like to answer, is it's really interesting to see these pictures and hear what you're capable of doing with this. But I was wondering if any of these observations or measurements are actually being folded into science programs now, either the ship tracking or any of the irradiance measurements, any of these things that there's lots of programs going on to monitor ice sheets and solar energy output, and it wasn't clear if this, the availability of this data is already being incorporated beyond just the project. Thanks.
If I can answer your second question first, and then Dr. Marshak will answer the question about ship tracks. We hope what you just said is true. What's missing right now is we're in the middle of satellite calibration procedures. And when we complete those in the very near future, we will have accurate data that can be incorporated into models of ice, cloud change, and various other things that are of interest to the earth science community. And yes, these will be incorporated into various programs. Let Dr. Marshak answer about the ship tracks.
Yeah, so ship tracks is a very interesting phenomenon that people started maybe to study it from 60s, and especially with satellite era. And ship release small particles, aerosol, that makes our cloud droplet size smaller and the lines of ship tracks more reflective. And they're clearly seen from satellites, and actually ship themselves does not change our climate because only 4% of the whole Earth is covered by ship tracks. But scientists use it as a laboratory to understand the effect of aerosol on cloud and then apply it to a polluted area of cities where you don't see quite clearly because of a gray area around. So how does it work to understand the effect of aerosol on clouds? So it's much more reflective.
One quick comment. There are a few science teams that are funded to work with this data, and we're expecting to start releasing the NISTAR data, and I assume others, to those teams within a few months.
Rick Lovett, freelance. Two questions. One short and very technical. What is your resolution on these images, spatial resolution? And the second one, more general, is, and it's not really what you're talking about, but one of the uses of this, as I understand it, is to give us early warning of space storms and possibly save our civilization. Could you elaborate on how good it's going to be on that? And is it operational yet?
So for the space science, maybe we could reference Dr. Zavo, who's in the front row, and answer the question on space weather.
And
but you can address first the resolution.
yeah, with respect to resolution, so the pixel size is 8 kilometers, and it's only one channel, 443, so we downlink data at the original resolution. All other 9 channels, they're average 4 pixels at the satellite, and so we downlink at 16 kilometers.
So I am Adam Sabu. I am the project scientist for the DSCOVR mission from NASA. You addressing your issue about space weather warning, the DSCOVR is not providing anything that we haven't done before. Currently, NOAA is using the ACE NASA mission. That's a research satellite, also at L1, making solar wind measurements, magnetic field, incoming solar wind particles. DSCOVR is providing continuity. ACE is already 20 years old. It was not built for a century type of service. So DSCOVR is the next, providing continuity of these measurements. It is not yet fully operational, though it's making measurements. So it's making the magnetic field and the solar wind plasma measurements. It is a NOAA decision. They are currently comparing parallel the DSCOVR and ACE measurements because they want to make sure that they are measuring the exact same things. There are a number of models that run based on this incoming data to forecast the severity of storms. So obviously they want to make sure that they will get the same type of responses from both measurements. When they determine that the DSCOVR measurements are at least equal or superior to the ACE measurements, they will probably switch over operationally to track DSCOVR. We expect this decision to be made somewhere around in the February 2016 timeframe.
Thank you. Are there any questions on the chat? Are there any other questions in the room?
Josh Halpern, Howard University. I have two related questions. The first one is, what's the situation now with the total radiation measurements as compared to total solar insolation, and when can we expect them? And the second is, when have you given any thought to launching a second DSCOVR on the opposing side?
Well, to the second one, to your last question, I would certainly entertain the possibility of trying to fly future missions of this type, but I'm not the one with the, I don't write the checks for that. We actually have a slide on that. Can you flip to that? For the band A and band A and band B channels. It's back in the, it's in the added slides at the back. The cavity radiometers are fully functional. We've been doing a lot of work in the last several months together. These are thermal instruments, and the amount of signal that we're actually measuring from Earth, we're a long ways away, is for the total channel is only 500 nanowatts. And for the shortwave, it's like 280 or 270 or something. It's back there somewhere, Bob. So those are fully functional, and we are getting data and working through the systematics of the instruments and developing the offset corrections. I'm sorry, what was I trying to say? It's a thermal instrument, and so the internal instrument. Did you give up? No. Okay, good. So anyway, dealing with the instrumental effects is a very important job, and we have good results for that. And on the imaginary slide, there are you can clearly see that we are pointing at the Earth, we're pointing at deep space, and we're pointing at Earth, and we can actually tell the difference. And the uncertainty goals for the total channel was to be better than 1.5%. Right now, we're looking at that one.
Second to last one.
Right now, we're looking at. Anyway, we are achieving that at this point.
Are there any other questions from reporters in the room? Okay.
Hi, Mary Beth Griggs with Popular Science. I'm curious, we opened up the talk with seeing some of that amazing aerosol going across from the Sahara, across the Atlantic. Are you able to also see pollution type aerosols, like the smog that we were hearing about in China last week? Are you able to monitor that from this spacecraft?
There are two different types of aerosols. One that's absorbed strongly in the ultraviolet, and those are volcanic ash, smoke, and dust primarily. The others are what's called mostly sulfate aerosols or scattering aerosols. Those are much harder to see in the channels that we have. So we will be able to see this in the form of a haze, but it'd be very, very difficult to distinguish from our instrument the haze caused by aerosols and the haze caused by, say, a low-lying cloud, thin cloud. The big difference in these aerosols, if you look at the edges of the of a cloud, they tend to be sharp and have some features that some geometric features that you can see, whereas the aerosols tend to be hazy. Other instruments or other channels, if we were to ever do this mission again and put on different channels, the answer is yes, we could see them. But this mission, the way this is, the 10 filters we have, this is probably not possible to directly see the sulfate aerosols.
Okay, thank you. And one more question. I was curious, you mentioned before that the EPIC instrument had been in storage for a while. How long was that? How long has this been going on?
So the entire observatory was put into storage in April of 2002. We pulled it back out in 2008 to do a survey and a study for NOAA, and then it went back into storage until 2011. And at that point, we had refurbished the Earth Science instruments, we reintegrated them, and then the project got started in the beginning of 2012.
Okay. Thank you.
Any other questions from reporters in the room? No, any other questions on the chat? Okay, that concludes our press conference. The next press conference will be at 10:30, Global Air Quality, the Impacts of People and Cities. Thank you.